These are my teammates Java and Joshua. So our project is called IoTGardening, and it's a full stack of complete project of home gardening irrigation system. And the gap was when we were researching for the project, we could not find a complete full stack. It was either just the soil moisture or just the water pump, but we could not find an entire complete full project. And this has a web app for the user interface. And the different sensors which we used a total of 4 sensors and 2 actuators. So we used a soil moisture sensor, and there are 2 types of soil moisture sensors. One is resistive and one is capacitative. But we are using capacitative as it does not corrode over time. And then we have a humidity and temperature sensor. And this is the updated DHT22 sensor. The old one was DHT11. And then we have a photoresistor, and this works based on resistance. As the light increases, the resistance decreases, and vice versa. For the water level sensor, as we know, water is conductive, so when the sensor is dipped in water, the circuit is completed and the sensor can sense the amount of water. And for the actuators, these are the 2 actuators which we use. The relay, it's used to convert high voltage to lower voltage. So the 12 volt adapter for the water pump which we're using is 12 volts, and the ESP cannot handle 12 volts. So we use a relay to convert from 12 volts to 5 volts. And for the water pump, it's a 12 volt water pump, and this one is the inlet, and that's the outlet. For the features of the ESP which we used Wi-Fi, the built-in Wi-Fi, for ease of communication, and we used an ESP uses less power communication, less power consumption. And the pros of using Wi-Fi was it's easy to integrate, and it's easily accessible. I mean, all of us we use Wi-Fi, and it's easily scalable. And for the cons, one of the cons can be that our project, it depends on Wi-Fi. So if the Wi-Fi goes out, there's no data transmission. And then, yeah.
So for a database, we used Firebase as our cloud platform. So our reason for choosing Firebase is because it provides real-time data updates, which is crucial for monitoring the soil moisture. And it's also low maintenance and also user-friendly. And as you can see in the picture over there, this is like a current example of what our database looks like. So we have like the water pump, which stores a Boolean, and the different sensors and their values, as well as the threshold. For the architecture, we implemented a serverless architecture. The primary reason for this was it allows us to concentrate on enhancing the user interface. And for the front end, we chose to use React. The primary reason we chose to use React was because like the many benefits that come with React, like you can combine the HTML and JavaScript into a single JSX file, and then it's also a component-based architecture. For the power consumption of the 2 ESPs and the 12 volt water pump was around 21.84 watts. Then over here is a quick estimate of the usage over the different time periods. So it would be 524.16 watts hours per day, and 3,669.12 watts hours per week, and then 15,724.8 watt hours per month, and 191,318.4 watt hours per year. So then from this we found out that the cost of consuming was approximately 191,318. The cost was $22.96 per year.
And since we have no incremental AI or machine learning, but we also create local storage for the training the model, and we're gonna use the logic regression algorithm to train it, because we also separate the condition in the good and the bad. It's binary classification. And what else?
Okay, for the task management.
So this is our Gantt chart. So from like the beginning of October, we initially started with just like researching and just figuring out what project we wanted to do. Then once we figured out that we wanted to do like the IoT gardening, we looked into like what all additional components, sensors, and actuators we would need, and purchased those. And then from there, we started working on the software. So we worked on the web application, implementing like the front end and the Firebase in the back end. And then after that, started testing and deploying. And then here's on the other side, you can see like the GitHub contributions. So you can explain the
Yeah, so Josh, he mostly worked on the web app. Me and Javed, we worked on the circuit and the sensors, connecting all the stuff with Firebase. And this is the contribution of our team for the lab demonstration. This is our web app, and the values are being updated real time. So, yes. As you can see, the soil moisture is at 89%. I collected the soil yesterday and it was raining, so its moisture is quite high. And that's the live temperature. Okay. And can you scroll down?
Yeah.
Yeah, you can update the threshold value, and when the value of the threshold is higher than the soil moisture, the water pump starts and it starts to pour water in the soil. Keep it at 95. I think I have to restart this. So what the threshold value does is it changes the value over here in the Firebase console, and when the value is higher than the soil moisture, the pump starts and it waters. And there will also have one more button called pour water, when the user can pour water into the soil. And the value, we have a Boolean value, and when the value is true, it waters the plant. I think it should work. Yeah, no. Sometimes it's not working correctly. It's supposed to work, but I think. But you can see on the reader that the value is, it's on, but I think there's a problem with the adapter, with the power adapter. Let's carry on. So for the future plans, first we have to test it with different types of moisture, and we have to test it in a dry temperature and a more wet humid temperature. And for the performance metrics, we have to test the accuracy with different.
Can you show me? Can you take out the moisture sensor out the dirt so I can see it change, like on the UI? Okay, cool.
Yeah. And we also have a light detector, but we could not put it on the web app.
Okay.
Yes. So, and for energy conservation strategies, we can use the ESP32 in deep sleep mode when it's not in use to reduce the power consumption, and we can integrate solar power to use renewable energy. And we can, once we have enough data, we can train the model to have an automatic watering schedule. That's our presentation. If you have any questions, you can ask.
Thank you.